All right, let's look at this. Hello? Hey, Andrew, can you hear me? Hello? Hmm.
Hi.
Hey, how you doing, man? Can you hear me?
You good? Yes, I can hear you.
Awesome. All right. Yeah, thank you for setting that up for me. Like I did see that. Do you want to just show me your chemistry stuff? Maybe we'll talk about the differential equations first.
Yes, I was a little late. I apologize. I was scanning in all of the
No, it's all
pages.
good.
Yeah, and it's kind of weird because I am trying to get this to turn into a PDF, but it's having problems. So I just decided to, since it's
Okay.
such a large amount of files, because they're
Let me
like
see. Okay.
Yeah, I
Um,
just sent the first there's like 2 assignments a week, which is
two
about
assignments.
average.
Okay. That's
Yeah,
fine.
and it is and then I'm just about to send the other one to you pretty much while we're talking.
That's fine.
But
Well, do you have the PDF like in your computer?
no, there's no PDF file. I do have the JPEGs of them. So
Okay.
I they're basically I just sent a zip file through Gmail, and when you unzip it, there'll just be the photos. Because I think Google Drive at least is having problems with saving PDF files in a folder. So
Yeah,
I just sent the images of the individual pages.
that's fine. I'll take a look at that later. For this, like the assignments for chemistry, when are they usually due?
So the first one that I sent T6 is going to be due on Monday, I believe.
Monday. Okay.
Yeah, and then the next one's going to be due Wednesday. And I mean, T6 is just about done. It's about halfway done.
Okay, that's
Um,
good.
but the other half still needs to be worked on. It's
I'll
just
I'll take a look at this like because I know it's like two subjects. It's not that bad. I'm taking a look at this homework actually. I thought I was actually gonna provide homework 1 to 3, but the correct answers are already there.
yeah. So it's just because it only shows you the correct answers after the deadline is passed.
Yeah, makes sense. Yeah.
But the current one, the 15 set, is you still have to figure it out. So,
Okay.
okay, I
I
just
think
sent.
that'll be good. That'll be good if we and then it's only, is it like weekly, the homework for math?
Yes, it's due every Sunday at like 10 like 10:30
Okay.
Eastern. So it's
Okay, that's fine. Yeah, maybe we can like do like this time we'll talk about this guy, and then I'll probably like we can go over maybe like T6 if maybe you can show me, but
yeah.
uh, and then like every week maybe we'll talk about, because like I wanna how it seems like there's a lot of like assignments he gives you guys, like for I was looking through homework 4, there's like 15 problems,
Yeah. It's
It's
terrible because I mean web work is a lot less helpful compared to because I've taken a lot of math classes, WebAssign and Pearson.
yeah.
It's they literally give you no help. So
Oh my, yeah. And then
it
for
was
chemistry, is it like so? Let me just get this straight. So the homework assignments for math, they have to be submitted online. Like it's like an input
yeah,
or
through a
okay.
server.
I see. That's like, as I was reading through like the prompts, there was like this weird like word, and I was like, what is this? So it sounds like you are entering it in.
Okay.
And then for chemistry, that's like scanning it and turning in.
Hmm.
Okay. Okay. Uh, let's talk about this first. Maybe you probably already started, like for this assignment, or
No, mainly
you
because
haven't yet?
it's
Okay.
I've pretty much really caught up pretty much up to now. Like I've
Okay.
caught up to speed finally, but and so next homework won't nearly be this much of an issue. But yeah, usually I get things done quicker, but not this
That's
semester
fine.
so far.
Yeah. There's a lot. Yeah, like I said, like for the usual, like when I was taking like these classes, it's usually only 4 to 5 problems, not like over that. It's brutal, especially like it's weekly.
Yeah. I mean, he makes them do in 2 weeks, but the only problem is that he made the first homework due 2 weeks after the start of the class, but he didn't open up until a week.
Week later. So you technically only have a week.
Yeah, but he
Oh,
offers 2 homeworks to do at once, but it's just really rough.
okay. I'm gonna do my best to maybe work with you so to give you like solutions every time. I think it'll be good, and then we'll talk about them. And then like, when's your first exam for these ones?
So the exam for differential equation, that one, I don't know. He just says there's one midterm and one final.
Okay, this is the typical. And this is a quarter or a semester?
This is a semester, so 15 weeks, I think.
Okay, so yeah, that shouldn't be that bad. Like a lot of the students I've had is like every week they had, or every 2 weeks they have like an exam.
Oh man.
So yeah, so I guess yeah, I mean it's gonna be a lot of homeworks to like pile up and kind of like memorize the steps in a way, or like just know the concepts and then understand it. But I think it's doable.
Okay.
How like before we go over like homework 4, how did you feel about homework 1, 2, and 3, like concept
Oh,
wise?
it not well. 3, I almost got no points on. 2 was okay.
Okay.
Though I still didn't get a good grade on it. It was the most completed. I think I got like a 60% completion on it.
Okay.
And number 1 was kind of not that great either. So yeah, not doing so hot in the class right now.
Okay. What I'm gonna try to do is so since I did all of homework 4 technically, let's just go over because like homework 4 will we'll apply those stuff obviously.
Okay, and I'm gonna open up the server real quick for the online homework real quick just to make sure, because it's kind of a weird format with how you have to input answers in a weird way. So let me just see if I can.
Okay, that's fine. Yeah. Like I do have questions on these ones. They're pretty typical. Like these stuff that he's asking you guys.
Mm-hmm.
It's just the procedure. Maybe getting like, because you guys have already gotten the second order, right, and like higher orders.
Yes, and he puts up huge lecture videos and does take up a lot of time, so it makes completing homework a real difficult thing. But anyway,
Okay,
so he's opened
but
up to 5 already. But anyway, 4. Let me just put 4 here.
okay.
So there's 15 problems. So yeah, the first problem.
Yeah. So this first problem right here, let me just try marking this up. So we'll talk about them one by one and see where it goes. So for this one, I guess what do you think you have to do? So
Okay.
he gives you this guy, right?
Mm-hmm. Yeah.
And then
So
this your professor, like a lot of when I took like ODEs, they usually do a lot of like acronyms: DE, GS, PS, particular solution.
general solution. Yeah.
And then this right here is and you're pretty much, the goal here is to find what K is, right?
I would assume so. I don't really quite know.
Okay, so I'll break it down this one. So
Yeah.
typically he gives you a differential equation. This is like the way like things are. So 90% of the time it's usually like that, and then you have to find like either the general solution or if you're given the initial conditions, right?
Yeah. Particular solution.
Particular solution, and then there's different ways of solving. The methods of using solving differential equations are pretty systematic, which is a good thing. It's just you gotta know like the different steps. Other times when like later on, I think it's like the last problem. He gives you guys like, and it's a brutal way of asking this question. Is like he gives you the solution, and then you have to find the differential equation.
Oh yeah.
I don't ever like find it that way. Like, oh, you should just learn how to do the steps.
Yeah. It's like when you first learn about integration. Like,
yeah, right. You have to do the opposite.
Mhm.
That is the derivative. Okay. So for this one, what I would do, I do have it worked out. So let's just look at this first.
Okay.
Can you see like the writing well, or do I need to like do this?
I can see it well.
Okay, like this.
Yeah.
Okay. All right. So if you look at this guy, this is. I'll just explain first like what I usually do for like when I teach this one. So the way I would write these, like maybe in paper and pencil before you answer it, is just do the givens, right? And this is the guy. And then what are you trying to find? Just so that like there's a system to doing it. And for
Hmm.
this particular problem, he wants you to find k small and k large. K being this exponent right here.
Okay. Yeah, I mean, it
Okay.
does. It says find the two values of k. Yeah, small and
Okay.
large.
Okay. And then you're probably wondering, why is it like so? Because for the most part, you're always going to be solving these polynomials. Like this is like the way of doing it, and this polynomial is a characteristic equation, right?
Yeah, and what is exactly a characteristic equation?
So a characteristic equation is so every time you do like a differential equation, he gives this to you in like derivative forms, right? Like,
Hmm.
and then this is just another way of like looking at this, and then you have this as this guy, and then this is t, yeah. So
Hmm.
what we do here is in order to solve for it, you need to write the characteristic. It's just that power. I mean, the theory itself, there's a derivation for it, but it's you don't usually ask it that way. It's just like, do you know how to apply it? And
Hmm.
how you do that is just by looking at the power of of your prime, or the your derivative degree, whatever, which
Right.
is like this guy has 2, and then this guy has 1, right?
Hmm.
And then this guy is just the regular variable, which is nothing, or to the power of 0 in
Okay.
essence. And then that's what it is. Like, you always want to write the characteristic equation of your differential equation, and that's just in a way for me to define it as just the polynomial version that you're trying to solve for your differential equation.
Okay.
And you're going to be solving a lot of polynomials, so back to your old algebra instead of like
Hmm.
calculus.
Yeah. Okay.
Calculus to algebra in a sense.
Yeah.
So it's not that bad. It's I would say like how I would like. So did you guys talked about, like, I guess because I haven't seen the lectures. Have you guys moved, because I know it's like first order and then constant coefficients, second order constant coefficients. What and then it's all homogeneous. It's all homogeneous.
Right,
Uh,
because it's equal to 0.
but what about like I didn't see any problem here except for like one, but they kind of briefly went. It wasn't like the main thing, but when what about when you're solving variable coefficients, not constant?
Okay.
Did he
I
did he did he go over that?
perhaps, but I just don't. I can't quite recall. Like he just doesn't really explain things completely, so I kind of get
Okay,
lost with the concepts. So
okay. Well, the way the category, like, so like stepping back is the way I would look at this is that there's different methods, and what they are is like there's the first order and there's the homogeneous, and then there's also the uh, not inhomogeneous, where
yeah.
you have this, but we're not gonna talk about that yet because I don't think you guys went over that. It's gonna be this guy where it's all 0, and these are all the steps, and then everything here is all your coefficients are constant, right? There's
Right.
no, because like when I say variable, this is in terms of x. All of these are
Mhm.
constant, not x. So that makes life easy. When you have like I guess a higher order differential equation that has constant variables, constant coefficients, and they're homogeneous, this is the way that you solve it.
Okay,
So
so this is you're mentioning that like other situations being homogeneous. So is this a non-homogeneous situation?
this is a homogeneous because there's
Okay.
when I say non-homo or inhomogeneous, the right hand side must equal like something else, not 0.
Okay,
That's
so
just what I
like
mean.
1.
Yeah, like some constant or some variable.
Okay. And when you say a higher order with other things, it would be like if we had a y double prime x or something.
Yeah, y double prime, and it's a function of x. That's a higher order.
Okay.
For this case, the order of your differential equation is the highest order of your, this guy.
Hmm.
Yeah. So, like, for first order, second order, like this one, I'll just talk about it and how you solve it. So this is a second order, right? Second order, constant coefficient, and then this is homogeneous. The very first thing is always know the steps is solving the characteristic equation. So when you transform the differential equation to a characteristic equation, this is what you get, and then in essence you're just solving for the quadratic because this is second order.
Okay.
Um, And then so, you know, you do that. And then this is when it varies. There's three things that can happen for the second order constant coefficient homogeneous. And then I'm not gonna talk about it conceptually. I just want to have you know how to do it. I think a lot of times the professor always talks about concepts and then not really how.
Mhm.
And then that's why I just like to skip on like, okay, let's just attack the problem. And then the more you do it, the concept just kind of like comes into play. It's like,
Okay.
oh, okay, now it makes sense. Because like all the derivation doesn't really matter unless you know how to apply
Yeah.
it. So the very first thing here is, so after you get the k, the polynomial, you solve for the quadratic, you're gonna get two things, right? Two roots, right?
Right. Because you got a plus or a minus.
Yeah. And then you know how many roots you have by the degree of your differential equation, right?
Okay. Yeah. So it's a second order.
Second order turns into a second order polynomial characteristic equation, which means you're gonna have two roots.
Okay.
So that's like kind of like the mindset of doing, like thinking about it, the flow. So after that, you solve for it, you're gonna get this two, and then, you know, a smaller k and a bigger k, but both of them are positive in this case. And when you take a look at this, this doesn't really ask you to move forward. This just asks you to find the roots. So I guess this is it.
Okay. So it's just pretty much almost like a modified algebra.
Yeah. I guess like giving you 15 problems isn't that bad because he does take you step by step. Like
Okay.
it gets harder as like you go on. Okay.
Yeah.
So
And I do want to just mention, I noticed that you have two windows open. So there's two Pauls.
yes. Okay. So okay, guys, I'll explain this. The way I usually do it is I'm on my iPad, like the one that you
Oh,
see.
okay.
Yeah. Yeah. That's like it's easier for me to write. And then,
Gotcha.
but the other Paul there is my evil twin, which is just on the side, just so that
Gotcha.
I can look at it. You know,
Right.
this is how my professor does it. Like he's pretty young and he does this too. And then sometimes when you write on you know, using a mouse, it's pretty bad. It's insanely bad.
Yeah.
So yeah. Okay. Does that make sense for number one?
Yeah. And that was marked as correct. So
Okay, perfect. So
excellent. Yeah. That makes sense though. It's just the first kind of step of the process.
so it doesn't really touch on like this guy, yeah. Like we didn't really touch like, oh, this K is right here, right?
Mm-hmm.
But let me just, I guess, go further with that, just so that
Sure.
it looks more like this guy. So like, when you have these two roots, what does your equation look like for your general solution?
So your general solution.
If you're, yeah, this is like one of, because so these roots are what? These roots are distinct, real, right?
Real. Okay. Real roots.
So this is type one. There's three types: distinct, real, repeated, real, and then complex, conjugate.
Okay.
And then so for this one, for a distinct real root, the general solution would look like this. So you have the, you know, obviously this arbitrary constant C1, right?
Mm-hmm.
And then like whatever you have for your any of these, I usually start with like the smallest to highest. So this K becomes, you know, this guy. And then you have an X, right? And this is the first solution. And then this next one is the second solution, which is you get your other one, your other K, and you put it right here. And this is your GS. So this is the reason why they have that.
Okay.
Because this is what they're trying to imply. So it's like,
Yeah,
oh,
you're
okay,
finding your Ks.
yeah. And these are Ks. And then in terms of like, you know, what variable you use for a characteristic, it really doesn't matter as long as you're being consistent. Not use Y, you know, obviously, or X.
Yeah.
All right. So let's try to look at this next one. So this is the one where I was a little like it's not that bad, but like if you we'll get to it, but I won't really cover it until, because I don't think you guys covered it. Is, you know, if you look at number 6,
Mm-hmm.
this one has T here, right?
Right.
This one is a harder one. All these 1 to 5s, these are easy. This is what we've been doing here.
So I guess that last one would be a.
The good thing about this though is it's only one, so you can just you know, process of elimination. Yeah, but I'll show you next time, like, because I want to like keep it in track where like you guys are covering the same thing.
Okay.
But this thing right here, this is what you call a like, you know, we talked about constant coefficients. This one is a variable coefficient because you have t, and t is your independent variable, right? And it you know, it's this is a y t function, and when you're using t and then it's also a function of t, then it's a variable coefficient. It's going to be harder. There's like, okay.
Yeah, so I've kind of been having issues kind of completely understanding, just a solid understanding of how you know what's an independent and a dependent variable. So
okay,
are independent variables always your, like if it's drawn in this form with just the abbreviated the y prime or whatever prime is your dependent?
Yes, and then whatever is prime is your dependent, because it's a function of something else, which is the independent. Yeah.
So for dy dt, y would be the dependent.
Yes.
And for same thing with a y double prime or a y prime or whatever.
Yeah. Whatever your I mean, like if you write it like this, like the full form, where you have the parentheses, every time it's inside, that's the independent.
Okay.
That's why like people usually write it like that. And if you do it the abbreviated form, it's like, oh, which one am I? You know. So yeah, I mean, there's no harm in like writing it this way. Sometimes I write it the long way, just to like convince myself, like while I'm working at it. It's like I'm not, and then I'm also not reusing the variable or any of them.
Okay.
So yeah.
So if you just had an xy equals 0, for example, would there be any way for you to tell what's the dependent or independent?
Like you mean like x and y, like that?
Just x and y equals 0. How would you know what is the independent and dependent?
For this one, like this guy, like when it's parentheses y.
Yeah, or just x times y.
In a way, I think you have to give you some indication somehow, because you know what I mean, like there has to be something else. Like they have to give you a derivative, maybe another, and then if the derivatives are in terms of what, x, right? Then this is, you know that this is going to be x. And if it's like a derivative of y, and these are all y functions, then you know that, yeah,
x would be dependent.
Exactly. Yeah.
Okay.
So it's just observation. Like you just look at it.
Okay.
But okay, let's take a look at, so this one, yeah, we'll cover maybe like 1, 2, and then not all of them, and then I'll skip to 6 just to show you what I did, or like kind of preview what you would do. Okay. So let's look at number 2. So you know how like this problem is asking you fundamental solution set? Like what is the fundamental solution set, right? And when it wants you to do that for a differential equation, you have to find, I mean, this is a concept, tell me if you guys touch on it, finding the Wronskian.
Wronskian, yes.
Yeah, Wronskian, okay. And then what did your professor say? Like, so if a Wronskian is not 0, right? Something like that. If it doesn't equal 0.
Yeah, if it doesn't equal 0, yeah, I remember there is some kind of formula, or not a formula, but a rule, a theorem.
Abel's theorem?
Yeah, Abel's theorem.
Okay. I mean, all of that is a lot of, you know, like mathematic, like concepts. I would just say the one thing you should remember is the Wronskian, like it's not really a formula because it changes depending on like the size, you know, the number of functions you're given. And it depends on like if it's your solution has like 1, 2, or 3, then it's gonna expand either 2 by 2 or 3 by 3. Like it's better if we'll go over it, but I just want to talk about the Wronskian first. So once the Wronskian is not 0, then that means that you have a fundamental solution set. If it is 0, then and then another way of saying if it's a fundamental solution set is they're linearly independent.
Okay.
Yeah.
Linear dependence and independence is something I don't quite know what that
What
means.
it means? Okay, I'll fundamentally like say it. So what it's like linear algebra concepts. You know, like if something is invertible, whatever. That's where it comes from. It's if like one function can be written as in terms of another function, that means they're linearly dependent, right? Like for example, if I did like y1 equals like let's make it simple. Let's not make it complicated. If this is like 2 plus x, right, and then y2 is like taking like I'm just gonna times this by 2, so it's like 4 plus 2x. Then like this thing, these guys are linearly dependent because I can write y2 as 2 times y1, right?
Yeah.
But if you're not able to write the other one in terms of the one of them, the other guy, then like for example, like this guy, 2x plus like 1, they're obviously linearly independent, right?
I mean, I would think you could, because you could solve for one of the x's and then substitute that one in for the like y2. You could solve for like the 2x, isolate the 2x.
Yeah, you could do it that way, like
that
just solving for it. But like I would say like the main definition is, can you just times it? Can you do that one operation? Not like solving for x, but like an operation, a multiple division or like adding, you know?
Right.
Yeah, that makes it like if you could write it in terms of the other, then it's linear dependent. If it's linearly independent, that means like there's really no like mapping, like simple mapping of one to the other. But that's the definition. But in applying it to what we have here, if the Wronskian is not 0, then you have a fundamental solution set, which is also equivalent to saying y1, y2, y3 are linearly independent. Linearly independent if it's not equal to 0. And then that's why you can write them. That's why you say fundamental solution, because they are unique, right? Each solution, this guy, where is it? This guy, this guy, and then this guy are not multiples of each other. It's obvious from this guy, right? You're never going to be able to write y2 in terms of y1.
I don't know. I don't quite know. I'm still kind of stuck over at the first part where you're talking about the fundamental solution set at the very beginning of the definition.
Okay, so like when it's asking, like I guess let's step back. Like when this problem is asking for fundamental solution set, like the definite, like don't get bogged down in definitions, because the definitions really sometimes the application isn't how you define it. It's like one of those things in math. Like there should be a mapping, but how you do that, like I said, that the only relationship between like the definition, if it's linear independent or linear dependent, is if you can write any of these guys as a function of the other by observing it, not calculating the Wronskian. You can probably say that they're linearly independent, because there's no way for you to write cosine in terms of like E, right?
Right.
Yeah, or the other ones.
So when you say one step to you can simplify it with one step to plug into the other to show they're linearly dependent. Would that one step also include taking a derivative? So like y2 and y3.
No, like it's just your mathematical functions like arithmetic, plus, minus, division, and then like because like when you take a derivative, it's a derivative now. It's another kind. I'm just talking about these guys.
Yeah. So basically, like if I were to look at just y2 and y3, I would still say.
Because like what you're saying is maybe you can get these guys, right? Obviously.
Yeah, and I'm aware that you can't do anything with the y1. I was just thinking like ignoring y1. I was just wondering kind of little more explanation on the definition of linear dependency.
Yeah.
I was just thinking because you could take the derivative of y3 to get y2.
Yep. You could do
So
that one, but like I said, it's very not too advanced as that. It's kind of
okay.
like have you taken the like the vector class where it's like
No, but I've taken calculus 3, which
kind of like
covers
that, yeah.
vectors.
Like if you know how like this guy can be like v1, right?
Yeah.
And then like v2, if it's like this guy, these are linearly independent. But like if it's a multiple, it's like similar as that. Like, and then the way you do that
Yeah.
is just times it by value, right? You
Yeah.
do that like one.
Like a 2. So 202.
Yeah, it's the
Okay.
same way, same exact concept, but now you're using functions.
Okay.
And then like the way I was taught differential equations, we kind of like combine linear algebra with differential equations, which you can. If you take a look at this, this is kind of like linear algebra right here, because you're finding the determinant, right?
Mm-hmm.
Yeah. Okay. Let me so that's concept wise. Let me just like go over like how, how do you do this problem?
Okay.
Okay, so you're given the differential equation. You're always given that most of the time. And it's asking you to find, this is just my way of like writing, because it's a set, right? Fundamental solution set. And this is just a set. So I just wrote it in terms of set notation, whatever. So I want something to be like that. And then what I'm trying, how I'm gonna get there is kind of the same thing as number one. You find your general solution. So you find your roots, and then this one is this is the other kind. This is complex roots, complex conjugate roots.
Mm-hmm.
And then for this one, what does your general solution look like if you get this guy?
Okay, so general solution, that would be k double prime minus 3k prime plus k minus 3 equals 0.
For the general solution.
For the characteristic equation.
Okay, so yeah, this guy. So
Right.
characteristic equation, and then there's many ways of solving for you. You could probably plug in this in like Wolfram.
Hmm.
Like it'll solve it for you. I really don't want to get bogged down into algebra, or you could just factor in, this group factor thing, and then you get these guy, right? This guy right here.
Okay, yeah, after you solve for k.
Yeah, and then so solving for k, how do you write this guy, this general solution, knowing the complex roots?
Okay, so where would you be referring to? What line on that? Above the green box?
This guy. How do you
Oh,
write this
down
one?
there.
Yeah, using this.
Okay. So there are two parts. So it's the
Yes.
C1 and C2. Is that for the plus and the minus there, or is that just for one plus? So you like, would you
Okay.
have 4? So would you have up to C4 or just up to C2?
Okay. So let's take that into account. Like, what this guy right here? If you have like this is a third order, right?
Yeah.
Third order meaning what? You have three different solutions, like fundamentally three different solutions. But in this case, you're thinking like, oh, it looks like there's only two, right? Because there's C1 and then C2. But the fundamental solution set here is you actually have like this guy, and then you also have this guy, and then you have this guy. And
Okay.
this is how you look at it. The complex roots it's a little weird, but for distinct real roots, it's easier to see. But when you have like this 3 plus and minus I, the form that I usually go by in like writing the general solution is when you have the characteristic equation roots equal like this type of form right here, plus or minus lambda I, where like this mu and lambda, this mu is always the variable in front of like, or the exponent of E, right? And then this lambda is this guy, which is 1. This is 1, right? in front of the I, but it's inside the cosine and sines.
Where are you pointing to on the page? Because like, okay, so lambda, is that inside the cosine?
So the lambda here, let me just use another. So lambda is inside the cosine and the sine. This lambda
Okay.
for this particular problem is 1, right? It's in front of the I, the coefficient in front of the I.
Right.
So
Okay.
so that means then the general form is you put it inside the cosine and the sine. These general solutions don't really, like, it's just one of those things like, okay, you have a complex roots, and then but your general solutions are dependent on the roots. Whatever form they take is dependent on your roots that you find for your characteristic equation.
What do you mean dependent on the roots?
So the root, like for example, this is number 1. Yeah, this is number 1. So number 1, you remember we found distinct real roots,
Right.
and there's 3 of these. There's 3 different types of roots that you can get. I'm just gonna write them down right here. So you have distinct, real, and then that's pretty simple, right? It's like two things that are different, and they're not imaginary. So when you get that, your general solution looks like this. I'm just gonna write it like YT. Your general solution always looks like this. It's like after you get a distinct real root, you always have to write it like this. And this is just an example. This is not any particular thing. Like for example, this is a Y1, K1, and K2. So this is the form of that guy.
Okay.
And then the second type, the second kind is repeated real. Does this one make sense? The distinct real?
Yeah, there's 2 things unique here.
Okay, good. So you just put in the K, or like the roots of your characteristic equation, as the exponent of your E, right?
Right.
That's like the method for distinct real. The method for repeated real is slightly different. We didn't get to that one yet, but it's like this. When you're saying repeated real, does that kind of make sense? I'll explain it though. Have you heard it before?
I've heard repeated roots, but I don't remember anything
Repeated
about
real,
it.
yeah, repeated real roots. Repeated real roots. So what this means is like you have like K1. Hey, let me just take a look at this. So you have K1, not for the distinct one, K1 doesn't equal K2. For repeated, K1 does equal K2. This type of case, repeated real roots, like when you're solving, just recall, there is a problem later on, I'll show it to you, but this is just a theory, is when you solve for like a polynomial and then you have something kind of like this guy, or why don't we make this K? You know how like when you do this guy right here, you know how like this, obviously this is what? This is 1, right? K equals 1. Like if you solve for the root, K equals 1, right?
Yeah.
But then you have this power right here. It's squared, right?
Correct.
So in essence, here, let me write it down and then like take it back. So this one means what? K equals 1, K minus 1 K times K minus 1 equals 0, right? This is the same thing.
Okay.
And then so this is what this means. But in solving for in the differential equation and then writing its general solution, you can't just say K equals 1 though, even though it is correct, right? K equals 1. Yes, right? The reason why is then you're discounting the other one. And how you do that is you have to say multiplicity equals 2. Does this kind of sound familiar?
Not the multiplicity part. What exactly does multiplicity mean?
Okay. So when it only comes in when you get a repeated real root. And then multiplicity just means in layman's terms, it's just the power of your polynomial. That is after you simplify the characteristic equation. So in this case, you're gonna get like a grouping of polynomials raised to a power. and then that multiplicity is that power.
Okay.
And
So
okay, so that's like, okay, I know what it is now. So how do I use it, right? So how do you use it is, first of all, so you see this, and then you kind of tell yourself, this is a repeated real root. I know that there is going to be a k1, right? A k1 equals 1, and then a k2 equals 1, right? And then k1 equals k2 in this case.
Okay.
Repeated root, they're repeated. It's 1 for both times. And then so that kind of like circles back to each other. You have a multiplicity of 2, you have 2 roots. The k's are the same for this case. So what does the ultimate question is, what is my general solution, right?
Yeah.
So for this case, we know what it is for the distinct real. It's this guy. It's gonna be kind of similar, but then this is a little like, in the beginning it's gonna be a little bit awkward. It's like, why are you doing that? Like, it's because it's just rules. It's like different things or different roots give you different solutions. Different roots give you different general solutions. So for repeated real, what we just talked about, it's gonna look like this. So you have C1 as usual, arbitrary constant. You have E as usual, and then you have K1 and then T, right? That doesn't seem like it doesn't. It's in line with this. It's pretty similar, right? The only thing that's different is this second part. So C2, the next thing, it's gonna look different from what we had, and then how different, depending on like if you have this as 2. I'm gonna talk about the 2 case and then I'll extend it. So when this is 2, you have to put T in the power of like multiplicity minus 1. E to the K2 and T. So in this case, that's just math, but then in my, if you're gonna just talk about it, if you have multiplicity 2, just put in T here, and then nothing here.
Okay. So is this going to be, so you mentioned the C1, E, is that to the K2 or K1T?
Sorry about that. C1 is K1.
K1T, okay.
Yeah. And then the multiplicity of 2, you need to put in another T here, but to the first power. Let me try to extend this to make it make sense. So what if you have a multiplicity of 3, right? So taking that, like, what does that mean? That means you have this case, right? Where the power here is 3, which means the multiplicity is 3.
Correct, okay.
Okay. And then we can even extend that. I mean, it's the same thing, polynomial extended. So you have K1 equals 1, K2 equals 1, K3 equals 1. So all of them are equal to each other. So why does that matter to us? Again, because of your general solution. Your general solution is gonna look like this. So remember, this was the form for multiplicity 2. Now this is the form for multiplicity 3. So you're gonna have this guy, K1 T plus C2 T E K2 T, and then C3. It's always 1 less than your multiplicity, T squared E K3 T. That's the one.
Okay.
Yeah, so this one, like, it's just like a bunch of rules. That's what I know in differential equations. Like, depending on like what you get, like after you do some algebra, this is the form of the solution.
Okay.
Does that kind of like make sense? Those are 2 types. I'm not talking about the third type now.
Okay.
So the easiest one is this, obviously. This one's a little like, okay, you just have to know that that's the case. The third one, so what do you think? Like, you have distinct real, right? And then repeated real. The third one must be something different. So it's a complex now. So this is complex conjugate or whatever, this is the one that we just talked about, but I just want to like, explain what it is. So the former characteristic is let me think. What would it look like? So then after you do the characteristic, you're gonna get a root. Let's just skip to the root. So the root in this case, as I said, is this guy, like a general way of like looking at it. is you're gonna see a root like this, and then like this mu and then lambda, whatever you have there. And that's why when you write your solution, your roots for your characteristic equation, write it in this form so it's so that you can pretty much read off the general solution from your root, and it should look like this. Knowing this guy, you should be able to like just write this down. So you have C1 e to like the mu, right, t, and then you have this cosine right here, and then whatever is lambda, you put this here, t, and then plus C2e mu t sine lambda t. This right here all came from, your professor probably talked about this, but it all came from Euler's formula. That's the theory, which I don't want to talk about it. It's just it's just derivation of why this is the case.
Okay. Yeah, the e to the kt.
Yeah. Yep. But yeah, like the form of your solution should look like this, which all of them are like that. Like depending on your roots of your characteristic, you can pretty much write your general solution.
Okay, and for the second power, you might have already like for the repeated real.
Okay.
You mentioned what it would be like if you had k minus 1 squared equals 0. You wrote it out. What would that look like written out for just the k minus 1 squared? Like I understand the kind of like the form that you wrote, the C1 e to the k1t plus C2 m minus 1 e to the k.
Okay.
Yeah.
Okay.
Would it be okay if you could write out what it would look like in the same way as you wrote the k minus 1 to the third?
Oh, that one. For this guy, like for this guy, isn't it this guy? For the general solution?
Yeah, but that's for the third power.
It's for this guy, yeah. For the second power is I see what you're saying. It's this guy, right?
Yeah. So
For the second power.
K1, K2. Okay. Yeah, I guess I didn't write that down. Let me get that written out because I didn't know where you got the m minus 1 from.
Okay.
Yeah, so let me just copy that over.
The rule, yeah. So the rule for this is, yeah, and like when you're looking at repeated roots, because like later on you have to it's not just that, like you know how you have like repeated roots, and you may think like, oh, this differential equation may only work with repeated roots, but you could there's times when you have to do this and then combine it with this guy. That's when it's brutal. So like,
could you repeat that again? I'm sorry.
Okay, let me repeat that. So you know how like, what if you had like a fourth order, right? This is your fourth order. I'm not gonna write down the whole equation, but when you have a fourth order differential equation, you have you have like 4 of these guys, right? You have 4 of these guys, 4 distinct, unique solutions.
Okay.
And then your characteristic equation, this is just arbitrary. I'm not saying like this is a case every time. But what if you had like k minus 1 squared, and then k plus 2 maybe, you know, and maybe k minus 3, right?
Yeah.
You have 4 roots here equals 0. This may be the case, it may not, but what are you seeing from here? You have 1. Let me change this so it's easier to read. You have 1 that's like a repeated root, and you have 2 that are just your first case, right? Distinct roots. So you have 2 here, you have 1, that's 4. You're gonna have 4, but C1, like for this one right here specifically, I guess since we're already there, I might as well write it. The YT for this one is gonna be C1E. What is that, like 1, right? 1 for, so that's gonna be
E to the 1T.
Yeah, so that's gonna be E, or C1E to the T plus, I'm not gonna do that. I'm just gonna write it so that
the C2E.
let's work with variables. So K1T plus C2E, C2T, C2T, E1, K2T. So that's,
Why would you get the t there in the front? Is that a derivative?
no, it's applying the repeated roots. It's a repeated root. It's a repeated root.
Okay, yeah.
So this is where I'm getting C1 and C2 terms. This is where I'm getting C3, and I'm gonna write these ones, C3 and C4. So C3 is gonna be E. What is that? -2? Yeah.
Minus
Minus
2t.
Yeah. Not to confuse you. Let's just go with what the actual K is. So -2t plus C4 E. What is this? This last one. It's 3, right?
Yeah, e to the 3t.
And that's it. And that's your general solution right here.
Okay, so you're only going to have a t multiplied in for the C2?
Yes, because you only account for it when it's there. For like, which root is this one? K1, K2, right? It's only for that guy. So C1, C2. C3, I mean, you can make this C1. It's really up to you, as long as you're accounting for all the solutions. You need to account for all the solutions, and that's why you have to write this guy, because these are the solutions that you get from this guy, and you have to write this guy because these are the solutions that you get for that guy, and this guy, the solution you get from this. So you have to account for all the solutions.
Okay. C1 e to the t plus C2t e to the t. And let's say if we had 5 roots here, but the first one was k minus 1 cubed, you would still have the same C1 and C2, but then the C3 would be the C3t squared e to the t.
You got it. Yeah. So you like what I would do, like, to set it up first. You could always, like, mentally do it, but like I would do this. This guy would have C1, C2, C3 terms. This one is C4, and then this is C5.
C5.
Yeah, that's like the practice of like looking at it. Eventually, you could just skip all of this, but yeah, what you just said, right? Like, it's just this guy. Like, what was it? 1? Yeah, 1 T C2 T E 1 T plus C3 T squared E to the 1 T plus what? C4 E to the minus 2t plus c5 e to the 3t. Pretty nifty though, right? You could just do that.
Yeah.
It's actually like that's why I like talking about like ODEs, because then like it's like there's so many different ways. It's fun, like how you can just solve for all of it by following some certain algorithm.
Yeah.
And all of this will be extended. Like now it's ODE, and then PDEs will have their all on its own their sets of like algorithms to solve for the differential equation.
Cool.
And that's why the way I would like remember these guys, eventually they're not gonna matter because you can just use like MATLAB to solve for it. but like now, it's always good to learn like the back end, because then you can program your own sets of like solvers. But right now I would categorize them like what I did here, like 1, 2, and then this is what you get if you have this guy.
Okay.
Because they're all going to be like this. It's always like this. Like there's certain conditions that you have to meet, and then those conditions will lead you to the general solution. All right. Does that kind of make sense? Like that's like kind of like a whirlwind of like second order solutions, homogeneous.
Yeah, that makes some more sense. Yeah.
Okay. So like covering this guy now, like wrapping that with Wronskian. How does it relate? So once you get to, change this. Once you get to this guy, you can just read off also the fundamental solution, but you have to check first. And then for a complex root, it's just that, and then your Freg terms, exponential, and then Freg terms. And then you have 3. You have 3 because it's a third order. And then how you want to check? I would check using the Wronskian. I'm gonna say this and then I'm gonna explain it. I kind of did explain it. Like if your Wronskian, your W is not equal to 0, then you have what you assume, from your general solution, your sets of fundamental solutions is correct. They are fundamental. If it's equal to 0, then this isn't a fundamental solution set.
Hmm.
And that's just really like, okay, if this, then that. And then how you find the Wronskian, so, you look at this, there's 3 things, right? Because there's a third order differential equation. Your Wronskian is going to be a 3 by 3. And it maps perfectly. 3 sets of solutions, you need to find 3 Wronskian, 3 by 3. If you have a second order, you have 2 fundamental solutions, then this is going to be a 2 by 2. And let me just do this. For a Wronskian, for a 3 by 3, did he kind of cover like what the terms are?
I mean, the thing is that you find each of your y's and then you take the proper number of derivatives. You put those in.
Yeah.
But like, I'm asking the same questions over and over again, but
It's fine. This is good. Okay.
okay. So a fundamental solution set is when your Wronskian is not equal to 0.
Yes. Yeah,
Okay.
that's correct.
And
Yeah.
could you kind of just quickly, because I'm pretty sure I'll just kind of recall my memory, but what is a fundamental solution set again?
A fundamental solution set, like fundamental by definition, means like it's linearly independent.
Okay, linear. Okay, yeah, linearly independent. Okay, got it.
Like in vector calculus, like your vectors can't be can't be multiples of the other. I guess for differential equations, that you just can't like do the same thing. You can't write one element as a function of the other, like a linear function.
Mm-hmm. Yeah, I haven't taken linear algebra yet, so I
Okay. Okay.
was not familiar. It's like every time I hear it, I can't really recall what those were.
Yes. So sometimes like yeah, it's fine. That's like the more exposure to it. I think linear algebra is like one of those things that I would say if you were to take a class, that's the class you should take it. It's really, really good. Because
I always thought it was interesting because I like matrices. They're like puzzles to me.
yeah, exactly. Yeah, you'll definitely love it, man.
Okay.
Because I would say like linear algebra, if you like that kind of stuff, you should take finite element as well. It's like that last thing. After linear algebra, you have to solve for these PDEs, and then a method for it is like finite element, which is really fun. Okay. So like, so that you're right. Like, so for a Wronskian, the first row is like all the functions of your solution set from your general solution. And then the second row is just the first derivative of those functions. And then the third row, because you have 3 solutions, is just second derivative. Let me just cover like, because like this is just jumping the gun, because you're doing a 3 by 3. But what if you had a 2 by 2, right?
Okay.
So if you had a 2 by 2, let's just say like this. What would it be? Like I've seen this before. Like let's do one where it's only like distinct, real, just to like cover terms. And your fundamental solution set would look like this, right? And maybe your K was what? K1 was 3, and then K2 is
K2 is 5.
Yeah. So like, see, it's always good to relate these things and kind of like talk it out and feedback, and then like, okay, that's what you mean. This relates back to this. This is a distinct real root. And then so, what is your Wronskian? You want to find if S is a fundamental solution set. So that's your question. Now, how you find that out is the Wronskian. So let's say this is what you do. So the first function is e to the e to the 5t, and then the second row would be what?
Just 3, like 3. well, 3t e to the 3t, I don't know. The derivative of e to the 3t.
Okay, and then so these things
T.
this means determinant. Like when you have like these things.
Yeah.
So a 2 by 2 determinant, pretty simple. If you get to like 3 by 3, not so much. You just cross this and subtract them. So like it's like 5e5t, and then minus 3e3t e5t, right?
Right.
And then so let's simplify that. That's like 5.
So you're just doing the cross product?
Yeah, in a sense, yeah. This is how you do a determinant, yeah.
Okay.
So like you cross these guys and you minus the cross of these guys. So let me see. This is 8t, right? I think that's right.
Mm-hmm.
Okay. And then you simplify this to the most simple form that you can make it. The reason why, because then you want to get that function where you want to observe it if it's actually 0, approaching 0, or like can it ever become 0 or not, and that's what you want. You don't want it to be 0. So let me see, what is this? 2e to the 8t, right?
Mm-hmm.
So this is your Wronskian. And now let's compare this to 0. So can e ever approach 0? Like, I guess you can make this, like, simplify it. Like you can divide by 2. It's still going to be 0.
Yeah, whenever you plot that, you would have a graph approaching 0.
Yeah, but it can never be 0, right?
I mean, the limit would be 0, but the value wouldn't be 0.
And that's the one. Like, it has to be the value because it's
Okay.
exponential. Yeah. So if this one, like the not this guy, you can obviously make t equals 0, right? And this is going to become 1. So this one can never be 0 by graphing it. I usually graph it. That's like the easiest way. It can never be 0.
Yeah.
So therefore, you can conclude that the Wronskian can't be 0 by just doing that. Like the 2 by 2s are really easy because then it's like, especially if it's like distinct. But so what does this mean?
It means it would be a fundamental solution set then.
Yep. And this is just not my way of writing it. You could do it. It's not. So what I would do is like, yeah, just say like, yes, it is fundamental. And this is right. Yeah. So that's how you know it's fundamental. And maybe you could look into, like, if you're going back to the prompt, you go look at these guys and see if you can find that.
Mm-hmm.
But that was just an example.
Okay.
So like that's for a 2 by 2, and then now if you extend that to like a 3 by 3, this doesn't look as bad now. The concept kind of draws itself into it, right?
Right.
It's just an extension. But the hardest part here is finding the determinant, which I kind of left that for you.
Yeah. I mean, it's not too bad because I was in my Calculus 2 class. She taught us kind of a different one because the way I see it traditionally written is you basically turn the 3 by 3 into a bunch of 2 by 2s.
Oh, the cofactor?
Yeah. Is that what we would be doing here?
Yeah, that's
Okay.
how you do it. That's usually like my method of 3 by 3 and higher. It works for
Yeah.
anything 3 by 3 higher.
Okay.
Cofactor expansion, yeah.
Yeah. And I know for anything above 3 by 3, yeah, you would have to do the cofactor. But in most cases, we're just doing a 3 by 3 matrix. So the way we did it was we have, we make the original 3 by 3, and then we take the first 2 columns of the 3 by 3, so the y1s and the y2s, and copy it over to the right side of the matrix, and
You could
then
do that, yeah.
and then just add and subtract them all together. You multiply each diagonal.
Okay, yeah.
Everything in each diagonal, add them, and then go the other way, subtract. So you would
Yeah,
get 6 terms.
you could do that. Just do it the way I would say like do the way that you're most familiar with.
Okay.
Uh, I don't know how, because like for this one, for homeworks, they just want the final answer, right? They don't you don't really need to show your work.
Yeah. But I mean, I kind of need to so I can figure it out.
Yeah, exactly. Because for me, have you used MATLAB before? Like
No,
MATLAB?
is it similar to like Maple or something?
Have you used Maple? Yeah, I know Maple
N-
too.
No, I don't use Maple, but I don't really have any kind of coding knowledge.
Okay, it's fine. Like, I would just say like, you guys probably have, because like it's a checker. Like I would say like if you were to do this, and then you want to check yourself if you, because a lot of things in linear algebra, it's not hard. It's just a bunch of like
Yeah.
arithmetic,
Hmm.
and then sometimes you get so bogged down into that, and then you're gonna make like very minimal, or like the small mistakes will add up, and like for you to be around the ballpark, I would say just like use maybe Wolfram Alpha can also help you.
Hmm.
It always helped me when like when I'm doing something and I know the concept, but once I start doing the arithmetic, tiredness kind of kicks in and it's like, oh shit, I should have done this, but I didn't.
Yeah.
Yeah, it's like one of those things, and it's always good to have that checker, the quality control,
Hmm.
to keep me intact with my math.
Yeah, I just don't have anything that I know how to use, and I
Okay,
guess I should probably get to know how to use something like that.
have you used have you heard of the Wolfram Alpha though?
Yes, I have. I just don't exactly know what I can, like, how I can access the right areas to verify my work and things, like trying to find the page to type in the computations and things. Like, I don't know the subjects of what to look for, I guess.
Okay, I would say like in terms of checking right now, if you were just simply, you could just do the determinant, and then just go with it. I'm just trying to give you like a checker so that like every
Yeah.
time, like it's always correct.
Hmm. Okay,
Yeah,
so it's
I'll probably
on.
I'll show you like how to use like Wolfram Alpha later on, maybe.
Okay.
Yeah, because then eventually, yeah, that one will really help you. Or maybe MATLAB. I'll show you MATLAB as well. Like if you guys are gonna be using that. Does your professor use any of these? Like maybe Mathematica? I don't.
No, though every single one of those I've heard of. I've heard people use Python.
Yes, you could use that too. Yeah.
Yeah, MATLAB, Maple, all these. They all are completely familiar names. I've just never used any of them except a little bit of Wolfram.
Okay, maybe we'll stick with Wolfram. Yeah, I'll show you Wolfram, and then Mathematica is Wolfram's product.
Yeah.
I have both. I have because, oh yeah, like I guess this is a suggestion. Like if you like doing matrices, like if it's something that you would like to like pursue, definitely learning any of those languages. I would say MATLAB. MATLAB is the best one
Hmm.
for matrices. Uh, just get like your free copy and just like try it, because then all the things you're doing here,
Yeah.
you can do in MATLAB in one step.
Okay.
Yeah. So if you do that, and then like it's kind of like, okay, now I know the theory and I know how to apply it in coding. It's not that bad. It's just learning that function.
Okay. Yeah, because I know
Okay.
there's some scripts that are kind of hard to know how to do.
Yeah. Try to like, yeah. There's a lot of YouTube videos on like MATLAB. Like it's one of the like those ones. Maybe just like linear or calculus applications of MATLAB, like those ones.
Okay.
All right. Does this run skin kind of like make sense now? Besides like the
Yeah.
determinant.
Yeah, as long it's just like trying to figure out. So basically, you solve the determinant and you try to determine if it's equal to zero, and that will tell you if it has a fundamental solution set or not.
If it's not equal to zero, yeah.
Okay. Yeah, and how do you know what your I guess okay, I was just thinking like how do you relate the I guess your answer after you determine if it's a fundamental solution set with which one of the six? So
One of
like
the one of the six.
yeah, so do you like to attack this problem? Do you focus on your answers given first to determine the
I
equation, or do you start from the equation to get your answers?
Oh, I see. Okay. Yes, that's a smart way of looking at it. I mean, I always the way I did this, like if you're gonna be like timed, yeah, do that. Like if you're learning it, do it the way I did it, and then kind of like look back and it's like, oh, do I have that? The reason why is like you don't want to just be like matching things. You want to learn the process.
Yeah. So basically, you worked with the
Yeah,
you
but if you're
basically worked.
if you're time on the test, definitely just match it and then try to skip steps as much as you can.
Okay, so I'm just trying to make sure. So you basically in this for this the written out solutions, you worked from the solutions given to match with the problem, or did you do it the other way around? Like, I'm just trying to
I
know
so
how I
so
can look at your solution.
okay. So I did check it back. I checked. So I did I worked it out myself first, and then I
Okay.
went back here, and I kind of like matched it. That's how I did it. But ultimately though, they're all the same. Like there's no difference really. Uh,
Okay.
I'm just trying to match like the after I did the general solution, and then I saw some terms there that's similar to like these guys, right? Like after looking at the general solution and I saw some terms, then that's when I assumed this guy, if that makes sense.
Hmm.
So like
Okay.
I looked at general solution, which I did on my own, and then I went here. It's like, oh, this looks like, oh yeah, and then when it says one, when this says one.
Yeah.
For this first one, it doesn't really have a one. It's this guy, so it's F. When it says one, that's just like C1 or C2, whichever one. Like it doesn't have like it's the constant. They're not gonna write constants here for fundamental. It's usually just like a number.
Okay.
Let's actually take a look at that one, like just to brush on it, where it's actually one. So like if you look at number three, like
Number three.
number three here,
Okay.
number three for number two, which is this guy. I'm just gonna skip the steps, but same thing, general solution, right? Right, the sun,
Yeah.
and then so this is a three. Again, it's obviously like three roots, three fundamental solution sets. When you look at the general solution, you can read it off. And what I did here is like the function in there, this guy, is going to be one right here. Because it's e to the 0, right?
Yeah.
So that's going to be one. So that's why this is one. And then, cosine t is going to just pop out and sine t. That's how you relate them.
Hmm.
Like, what I would do is like find the general solution, look at your givens, and then this is how I did it. Like I would just read off the fundamental solution from the general solution.
Hmm.
Does that kind of make sense?
So yeah, you basically find a fundamental solution. I mean, like in these, we determine the possible solution sets. I mean, the the solution sets. Um, did we get those values before we verified with the Ronskin, or did we do the Ronskin first to get the
Okay.
solution sets?
So what I would do is, because then you wanna get somewhere, right? You wanna get this guy, right? And
Right.
because you're given this guy, and if you're given that guy, like I said, like the very first like run through it, because if you have time, is do like general solution, Ronskin, fundamental solution set, and but then like in order for you to get the y1s, the y2s, and y3s, you need to read it off from this guy first, from the general solution, because you need these guys in order for you to get the Wronskian. And this y1, if it's complex, is like it's just reading it. But this one is e to the 0, so that must mean it's 1. And then this one is the cosine t. This one is the sine t. You're gonna need this guys to check the Wronskian.
Hmm. I don't know. I'm just kind of confused on.
Which part? Which part?
I guess it's just
Let's take a look at this guy. Maybe it'll make more sense. So
okay.
this one, because the complex one is a little weird, because then it looks like you only have two solutions, but there's actually like three. But that's just how you look at it that way. If you take a look at the second one, that's the differential equation, and then you find the general solution, and then this one's a little bit easier because then you have these three things in here, right?
I don't know.
So like, you know how when you solve for the general solution from this guy after doing the characteristic, you get like a general solution, right?
I guess so. Yeah. I just kind of, because it's kind of, I know it's just time issue. It's just like, I guess the skipping the steps thing. I think I just need to.
Yeah. It's one of those things like you gotta just like go after you do it 5 times maybe. it's gonna kick in. But does it, like, what I'm saying is you always have to write the general solution though from the differential equation, right?
I
That's kind of
I understand that. It's just, I guess the
this,
steps to get our general solution. I just don't know
okay.
how to do.
Yeah, just do a few of these. I kind of showed you the 3 types, like the one that we talked about. They're all in this homework. There's 3 different algorithms to solve for this guy. And then this one has the multiplicity. Do you remember that one?
Multiplicity of 3. Yeah, it's cubed.
In front of the E, right?
I'm sorry, I couldn't hear what you said.
Okay, so if you have multiplicity 3, that must mean that you need to add the variable, the independent variable, right, in front of the E. The T is
Yeah,
the
I guess the 1, the t, and the t squared.
yeah, that's like just the algorithm. That's what you have to do if you have a repeated real root, right?
Right.
Exactly. Okay. Yeah, that's what you have to do. And then, but then that's like one concept. You gotta, like, I guess, set in stone first, find the general solution, and then everything kind of just everything just kind of comes from the general solution. Like all other questions, kind of, you have to like master like finding the general solution first. But like, let me see first, like after you get the general solution, because the next step for this is finding the fundamental solution set, right?
Yeah.
So for this guy, it's really simple because it's just these terms from your general solution. These are the ones that you want to have, which is y1, y2, and y3, right?
Okay.
Yeah, if you do like these like very, step by step, it's gonna make sense. It's like, it's gonna take some convincing in a sense because it's not natural yet. But the more you do it, it's gonna become more natural. Like, oh, okay, that's what you do, and this is what you do.
Okay.
But the one thing first, like the very, because this question actually is something I don't like too much, because like in the first question they asked you to not even solve for anything yet, right? They just asked you to solve the characteristic equation, right?
Right.
And then the second one, they asked you to do a Wronskian and solve for what is the fundamental solution set, which is like jumping the gun. Like you didn't even solve for anything yet.
Yeah.
So maybe it should be reordered. Anyways, it doesn't matter. Like we talked about it. So yeah, that's what you do. I can cover this more if you want, but each one of these really is just solving for the general solution, and then checking the Wronskian, and then knowing what your fundamental solution said. That's going to inform you.
Okay.
Same with this guy. Maybe I shouldn't cover number 6, but like that, it's even more complicated. Because like when you look at this guy, right, the number 6.
Yeah.
You remember I said it's a variable coefficient.
Variable coefficient.
Yeah. I think you guys didn't cover this yet because like I said, I only saw it here, and it's probably just a preview. I'm not gonna really explain it, but I'm just gonna point it out. You will talk about reducing roots. These are the algorithms. These are the algorithms for variable coefficients, Laplace transforms, and indicial equation. This reduced roots one is the one that's commonly used. This one is a little complicated. This one is sometimes used. But it doesn't matter because for this problem, it's the only one left. After you do 1 to 5, C is the only one left.
Mm-hmm.
So that must mean it's C without even doing it.
Okay, so does that say the last one, is that individual equation?
Sorry, indicial.
Indicial. Okay, so it's like you index it?
Yeah. But like, I wouldn't worry about this one so much. Like if you want to, I guess like, learn about it, look for this guy, reduced roots.
Okay.
For variable, coefficient, differential equation.
Okay.
Yeah, we'll cover this one like next if you guys cover it, because it takes a while. It's like one of those awkward algorithms. It's like, why are you doing like what we're doing right now? To relate it, what we're doing right now is what? Constant, right?
Constant, yeah.
Coefficient, differential equation. Easy. This is hard.
Okay.
So we'll cover it next time because I'll really dive into reduced roots if there's a homework problem on it. Okay. Did you wanna talk about just a few of these, or maybe this guy, or let me jump to one. This one maybe it's not that bad, right? What do you think?
Mm-hmm. I
Number
guess.
3.
I don't know. I'm guessing you have to determine whether you use a determinant and see if it hits 0, because I mean 2 looks like it's hitting 0.
Yep. Yeah. That's a smart way of doing it. What I did is pretty much I kind of just like arbitrarily graphed it from the general solution.
Okay.
The general solution will inform you like how to graph it. So pretty simple. I mean, it's just doing that like the step of general solution and then graphing and matching.
Mm-hmm.
Okay. Let me breeze through these. Like I don't maybe just one. Like I'll cover like one problem here is like it kind of technically covers all of them. It's if we take a look at, let me see. Maybe let's look at 4. Because this is the full one. This is like IVP. Did your professor talk about IVPs?
Yes, a little while ago.
Okay. Yeah, you get introduced to this when you're doing like first order, right?
Yeah.
First order. And then you could do second order. IVP is just a term for all differential equations with initial conditions. Okay, so the main thing for doing like an IVP is this is like the complete like formal way of like stating a differential equation is you have a differential equation, right?
Yeah.
And then you have what do you need for a differential equation? Like since you have 2 time, it's like second derivative of time, right?
Second derivative is, I guess, yeah, it's a time derivative. Yeah.
Yeah. Right now, like time. Like most of it is like OD is time derivative. And so since you have 2, second order differential equation, second derivative, that maps into telling you always need 2 initial conditions. The degree tells you, the degree of your differential equation tells you how many initial conditions you need.
Okay.
And like, this is like the basic step. Like you have the differential equation. If you're not given the initial conditions, you can only go up to like the general solution, the GS. If you're given the initial conditions, it becomes an IVP, initial value problem. And then this you can map into, now you can solve for a particular solution. Now you can get the particular solution, the PS.
Okay.
Not just the general solution.
Okay.
So that's like the concept, and now we'll talk about it. So like when you have like so the very first thing here, as you always do it, is you always need to find the general solution, right? You always need to find a general solution by solving the characteristic equation.
Mm-hmm.
And then so for this one, this is the easy one. It gives you distinct real roots. So since it gives you distinct real roots, this is what you get, right?
Yeah.
You have 0 and then -5. And then e to the 0 is 1, and you can simplify that. And then so now you want to find the next thing, the second step after finding the general solution is you want to find your, I mean, it drops out like in front of you because like these ones are arbitrary, right? C1s and C2s.
Mm-hmm.
So since they're arbitrary for the general, they have to give you something. And then that something is the initial condition. So initial condition, I mean, you could use this. What you have to do, first of all, when they're giving this to you, is the main reason why they're giving this to you is because you're solving for C1 and C2.
Okay.
And then how you get those constants is you need to apply what they're giving you, the conditions. This one is like a zero derivative. So you can just pretty much apply your main general solution. This one, on the other hand, is a first derivative. So yeah, I would do this either like you knowing that I would just take the derivative of this guy right away. So you have those two things to work with. And so what I did here was I used the first condition, initial condition. And how you just do that is like you plug in what? You plug in t for 0, right? You plug in t for 0 in the general solution. Sorry about that. Why is it? There you go. So you plug in t.
Okay.
Plug in t here in your general solution, which is this guy. The t is this one, and then you simplify, and then you make this equal 1 because that's what we have, right? This is equal 1. And then so this simplifies to 1. So what you have in the end, if you want to simplify everything, is C1 plus C2 equals 1, right?
Yeah.
So that's good. That's your first equation. In the end, how this is going to look like is you have two unknowns, right? You have two unknowns here, right?
Okay, wait, hold on. So C1 and C2, how are those both? So one is equal to 1 and the other one's equal to 0, or
What are you talking about? For which one?
like, I guess I don't know how you got C1 and C2 from just one of the initial conditions, or like
This guy. Okay. I would just, like this is our general solution, right?
okay.
Just using the first condition, plug in 0 for t in here, and then like see if you can get an equation out of it. They're not both equal to 1. It's just an equation right now.
Okay. So it's just a rule that C1 plus C2 has to equal 1.
Exactly.
Okay.
This is just an equation. This is not like C1 and C2. It's an equation. It's pretty much your first equation.
So it's just a definition C1 plus C2 has to equal 1 always?
Yes.
Okay.
But then, like thinking back about it, like you have two unknowns, right? C1 and C2.
Yeah.
The initial condition, the first one, gave you one equation. So that must mean you need another equation, right, to solve for both of these guys, C1 and C2. Right? You need another equation because there's two unknowns.
Okay, what equation are you talking about that tells us what C1 and C2 are?
This guy.
Yes. How do you know that the C1 and the C2 is equal to 1?
Oh, the reason why it's equal to 1 is just applying the initial condition, the first one, this guy.
Oh, okay.
after you apply that, you plug in t for 0 inside this guy. And then, this is it, right? C1 plus C2, e to the negative 5t, right?
Yeah, so since y of 0 is 1, then therefore C1 plus C2 is 1. What about for the y prime? When does that come in?
So you apply initial conditions, like there's y and then y prime. You apply them one by one. So
Okay.
after you get the result from the 1 equals C1 plus C2, this guy, you put it on the side for now, and then let's work with this guy, the second one.
Mm-hmm.
So you're putting that one on the side, and then you look at this guy, right?
Yeah.
And then now, like I said, you can either find the y prime later on, or like right now, beforehand, or like right now. Like this is what I got, right? So this is just the derivative from our general solution. I take the derivative of this guy. I'm gonna get negative 5, right? C2 e to the negative 5t.
Mm-hmm. Yeah.
So that's this guy. And then why did I want to get the first derivative? Because this guy is given the first derivative.
In the first derivative.
Yeah. And then so you just follow what it tells you. You plug in t, 0 for t, in the first derivative equation, and you make it equal 1. So it's equal 1, right?
Yeah.
And then it seems like the C1 disappeared. So you could probably use this equation. You could have used this equation first. But I usually just, I usually just apply them like from the beginning, like 1 and 2. And from this guy, you got C2 equals negative 1/5. This is the second equation. And since you got this explicitly, now you can plug this back into the first equation so that you can get C1.
Okay. So the 1/5, and then I guess plus C1 is equal to 1.
Yeah.
So C1 should be plus 1/5, or
Yep.
okay, I guess.
Okay, and then so what did you get?
I mean, let's see. So negative 1/5 plus C1 equals 1 is just going to be 11/5 as our C1.
I got let me see, 1. I got 6/5. Isn't it 1? It's minus 1/5.
Oh, it is 6/5. Okay.
Okay.
C1 is 6/5.
And then that's pretty much it. Like, so what was that? Like, I guess recalling what we just did. We did we found the general solution. We found the arbitrary constants. And then what's left? What was it? What was this question asking us?
So it says find general solution and find particular solution.
Yep. And then so once you have when you got the general solution in the beginning, once you have the arbitrary constants, you just plug them back in the general solution, the C1s and C2s. And then you get this.
Okay.
Yeah, that's technically the way I usually see it. Like, asked a lot. Like, do you know how to apply the differential equation algorithm for this type of differential equation? It's an IVP problem. All of it is an IVP problem. An IVP problem just tells you do this. These 3 steps. They're very pretty common with all the differential equations.
Okay. Yeah, what I think I'll do is I'll probably just plug in these answers in, get this actual, like, I guess the homework turned in on time.
Okay.
complete, and then basically right after just work through this, your solutions and just get to understand these.
Okay. I think that sounds good. And then for this one, or because this one is due. When is this due?
It's due on Sunday at 11. Oh, yeah, 11:59 Eastern. So
Okay. What I could send you I'll send this to you actually, yeah, because you said you couldn't access it, right?
yeah, I guess it's just because it's all in um, it's like in a directory. So for some reason,
Yeah.
it just wants to show the directory, but it doesn't let me open each individual file.
Yeah. I'll send it to you individually, like each one. Because I have it, and then I'll just like attach it to an email.
Okay, great, thank you. And it's just kind of that's the downside with email, is the file size is kind of limited. So
Yeah.
only 25 megs.
I can probably just I usually use like WeTransfer. Maybe if I exceed it, I'll just give you like a WeTransfer,
Okay.
like a link. Okay. If there's anything there because like some of these steps, the new ones, that's what I covered in the solutions. And then like for the steps, I know like I kind of skipped some because I know they're very similar, like to
Mhm.
number 4 or number 9. You're gonna see it. Just
Yeah.
just ask me if you need me to like solve that problem.
Okay.
Yeah, because I for that one for some of these I just said like C number 4 or number 9. You'll see what I mean.
Okay.
And then for your chemistry homework, I'll take a look at that and provide like for T6, right? That's the first one due.
Yeah, T6. That one's due Monday. Would it be possible if we could have another meeting on Sunday?
Yeah, that's fine. I only have like one appointment on Sunday. Yeah.
Okay. Yeah,
What?
whenever it's okay for you is probably okay for me too, because
Okay.
I can adjust.
Let me check. Let me check this first. Sundays. So in the morning, you want to just do it on like, I forgot what's our time difference? Is it like
It's a
two?
I'm 2 hours ahead, so
Okay. Do you want to do like? Because I have one at like at 2, I think 2 to 3 in my time.
okay.
Maybe like 3 to like 3 to 4, or how do
Yeah,
you want?
3 to 4 in your time. Yeah, because I mean, these are like kind of like tutorials, so
Yes. Yeah. Let's.
it's not too bad.
So yeah. For that one, did you wanna cover like the chemistry one or more of these guys?
Probably the chemistry one. I'll let you know if I have any questions for the differential, probably tomorrow. He
Okay.
also is going to have a Zoom meeting where he's going to answer any questions you have, so that can
Oh,
also be
that's
help.
good. Yeah. Okay. Yeah. Just shoot me that, and then I'll send this to you, and then I'll also send you the solutions to T6. That's my second email, I guess.
Okay, yeah, and I mean, you can maybe look over what I've written because I've filled out about half of it, but I actually went to my campus early for the lab, so I actually was able to get some information for the T6. So
Okay.
half of it's done, but the other half isn't. So I
Okay.
think the first half is okay, but I don't know for
Yeah,
sure.
it's fine. I'll take a look at it and just kind of just explain if there's fundamentals. And for every time I'm looking at this, it always tells me it's an hour and 30. I can't do like an hour. Is it fine to do like from 3 to 4:30?
3 to 4:30. Yeah, that
Okay,
works.
I'll just book it like after this. Okay. Andrew, yeah. I'm hoping like this is. Do you like the way I'm like presenting this, or do you want it to be like just computerized, like written like this is like it's more effective?
Yeah, it being written out is pretty good, I think.
Yeah, and it's much faster for me because then I could just chicken scratch, but then obviously I'm explaining
Yeah.
it. Cool. All right, I think that's good. I really like this because then it's like a twofer. Like I've done a lot of like tutoring for like chemistry, physics, and then like this guy.
Yeah.
So yeah, let's do that, and then I'm hoping I'll help you out with chemistry as well.
Okay, great.
Cool. Hi man, have a good one.
You too. Thank you.
Yep.